guess you all see my screen now.
Yep, everything is nice.
If this participants window bothers you, just close it. I have just closed it. So, Sasha, thank you very much for the invitation. It's I wish we could all gather and discuss more science in person, but unfortunately, this is not the case right now. I hope in the future we'll be able to. So, I propose to Sasha to present some recent results that we have been working on in some type of billiards named polygonal channels. And the aim here is to study diffusion and scape properties from such geometries. I will start very general, giving you the motivation but also the mathematical and physics motivation of the problem. And then I will show you some of the results that we have obtained in this problem. I don't know how this is, how you want to organize this, but please just interrupt me as much as you want. Don't wait to the end to interrupt me, since we are a small group. I think sometimes it's better, okay? So these are the type of problems that I will try to deal with, polygonal billiards, in which you have certain initial conditions, and these initial conditions disperse along this geometry. So, okay, so this is a particular case of billiards, which most of you should know what it is. By billiards, I mean simply the free flights of particles inside a container, with a certain geometry. So the particle flies freely and then it bounces, usually specularly, on the boundaries of the geometry. And this geometry obviously determines the dynamics of the particle. It can be chaotic, non-chaotic, depending on whether the geometry is convex or dispersing or even neutral, right? So the interest in statistical mechanics of these models is that they are natural models to study different phenomena like dilute gases, conduction problems, heat and mass problem, etc. No? There is a particular problem which is naturally modeled by billiards, which is that of transport through porous media. No? By porous media, I mean a material which is made of regions of connective empty space, of porous, and particles can move through these pores. So usually, what one is interested in is to try to understand the transport properties and the transport characteristics of a flow of particle, either a liquid or a gas, when it crosses a porous media. This is a very long-standing problem, still unsolved. It's difficult. It has many difficult mathematics. They can be as difficult as you want. So to define a bit more the problem, in this porous media, we are interested on those for which can be studied in the nuts and gases, or at least it is the limit in which billiards can be a good model. So by Knudsen regime, one means this is a situation in which the mean free path of the particles evolving through the media is larger than the characteristic length scales of the system. So if the mean free path lambda is larger than the characteristic length of the system L, then as a consequence, what happens is that the collisions between molecules are very few compared to the collisions between each molecule and the walls of the porous, right? And that is the limit in which one could, from a mathematical point of view, model such a situation with billiards, right? Because they do not interact. So they just interact with the boundaries of the billiard. And in this also works out of beyond the hydrodynamic limit. In the hydrodynamic limit, obviously log thermal equilibrium holds, which means that we have a good separation of scales between space and time. And in such a case, an approach with billiards is not possible. However, for very small systems, like for nanoporous materials, nanoporous membranes, local thermal equilibrium breaks down. And this is, again, the general case in which the interactions with the walls of the container are more important than the interactions between molecules themselves. So this Knudsen regime is very interested in many areas, in physics, in chemistry, in technology. For instance, to study heterogeneous catalytic processes over porous catalysts, or to study processes for molecular transport in nanostructured materials, for drugs delivered in the human body, or for to study rarefied gases processed in the atmosphere. So it's quite a wide, broad applications of this sort of billiard limit, the Knudsen regime. Okay, and the question that I want to address today is how does the geometry of the porous, how does the geometry of the billiard and its dynamics impacts the diffusion process or the transport of particles through these billiards. Okay, so concerning geometry, there are several characteristics that are important, as you can guess. One is the shape of the porous, because, for instance, if the porous are like this, I mean, the voids in between these circular obstacles, which is a well-known model, the Lorentz gas, and you consider a gas of non-interacting particles evolving here in this two-dimensional billiard, then in such a case, these particles will diffuse. They will normally diffuse as if they were a random block or a Brownian motion in time. And this is due to the fact that the geometry of these obstacles is dispersing, so the dynamics is very chaotic, and that induces some sort of diffusion in a certain limit. The counterpart of this is the well-known Ehrenfest-Wintry model, in which Ehrenfest substitute the circular obstacles by square obstacles. And the reason for that is that for a square obstacles, the dynamics is completely different. Here you don't have any chaotic flow, all Lyapunov exponents are zero, and there is just linear separation of trajectories when they hit an obstacle near the corners, right? So from a dynamical point of view, these systems are very different. And what would it interesting to know how the transport is affected depending on this geometry. There's another geometrical aspect which will be important for the sake of transport, which is whether you have this sort of infinite channels in the obstacles, right? If you have these infinite channels like here and here, or the vertical channels here, this means that trajectories, that the length of the trajectory between two consecutive collisions with the billiard, with the obstacles, can be arbitrarily large, right? And that has as a consequence that the mean free path of the gas of particles can be not very well defined, because you may have essentially infinite trajectories. So what we say that if we have these infinite channels present on the billiards, this means that we have some sort of infinite horizon, in the sense that there can be arbitrarily large ballistic trajectories between two consecutive collisions. In the opposite case, like in the one I have tried to design here, you have finite horizon in which there is a maximum size for the length of the trajectory between two consecutive collisions. Okay, so the horizon, whether it is finite or infinite, will certainly enter into the description of transport. Okay, so for the sake of transport, I'll just give you very general statements. So normally, one study diffusion is because one is studying the density of particles that are at time t at position x, and Fick's in 2 centuries ago showed that this density of particles evolves in time accordingly to a diffusion equation, which solution if we don't consider boundary conditions, which is the easy case, it's simply a normal function, a Gaussian, right? And since it is a Gaussian, this is what is called normal diffusion. So this is the usual diffusive transport that we are used to, in which the variance of the Gaussian determines the diffusion coefficient, right? In terms of the variance of the particle displacement. And importantly, we see here that for diffusion, the variance depends linearly in time. So it grows linearly in time, and the distribution therefore gets broader and broader as time passes. Since it is always Gaussian, then the only moments that are important are the mean and the variance, the second moment. This is usually how one study transport in an experiment, which is to study the fluctuations or to obtain the variance of the particle displacement, which is what we call the mean square displacement, right? And so one tries to understand how this mean square displacement evolves in time, and if it, in the case of diffusive transport, it evolves linearly. It evolves linearly in time. However, this is not the most general case. Particularly in systems at nanoscales, the transport or low-dimensional systems in general, transport is anomalous, meaning that the distribution of the particle displacement is no longer Gaussian. No? In general, we will refer in terms of the mean square displacement of the variance of the displacement, we refer that the transport is anomalous when the mean square displacement grows either faster or slower than linear, right? In such a way that the exponent here, that the scaling exponent of time is not 1, as in the diffusive case. In such a more general situation, one can always define a generalized diffusion coefficient, and depending on the values of nu, of this scaling exponent, we will have situations in which the mean square displacement grows slower than diffusion, which is the so-called subdiffusive regime, or faster than diffusion, which is the so-called superdiffusive regime. So this is what one can learn from the mean square displacement, but obviously the properties of the fluctuations in an anomalous diffusion case change. I mean, this anomalous transport reflects also on higher moments of the distribution, not only in the second one. So in general, the fluctuations are no longer Gaussian. And if the density of the particle displacement satisfies certain scaling variance, like this, in which we can have some spatial and temporal scaling like this, if this scaling balance is satisfied by the density, then one can easily compute that the arbitrary order, the moments of arbitrary order of the displacement, moments of order p, are proportional just by doing a change of variables, are proportional to t to the order of the moment times some times the exponent gamma, that is the exponent that enters into this scaling invariance of the distribution. In particular, for instance, the mean square displacement would be given by t to 2 times gamma. Okay. Now, I say this because even though this is very natural to find, and this is what we find for a Gaussian distribution, for instance, which gamma would be 1/2, and therefore the mean square displacement would be linear in time, this is not the most generic case. The most generic case was discovered or described in 1999, which is the so-called strong anomalous diffusion, no? In which the previous scalings that I show you here, that this gamma is no longer constant, but it has a dependence on the order of the moment of the displacement. No? This, for instance, is observed generically in many different systems, but let me just tell you, it's observed in billiards with infinite horizons. Again, here we have the Lorentz gas. And here what we are computing is precisely this exponent. And we see that if the horizon is infinite, the first two moments, the first moment here and the second moment, which is nothing but the mean square displacement, they evolve as if the transport was diffusive. So if you measure the mean square displacement in the Lorentz gas, you obtain that it is diffusive with certain corrections, but always diffusive. While if you consider higher moments than the second, like the third, fourth, fifth, sixth, and seventh, they belong to a different branch. They behave differently, and they are more determined. Their statistics is essentially determined by those very long trajectories that move along these infinite channels, right? So the statistics of the shorter fluctuations is determined by the dynamics, which is determined by the periodic orbits between these obstacles, but the long range fluctuations are characterized more by these very long flights. If we close the horizon, for instance, if the radius of the disk is larger such that the horizon is finite and you don't have these very long trajectories, then you see that all moments of the displacement scale homogeneously with this parameter gamma, which in this case is constant, and it gives you again diffusion. So this is something much more generic, and the type of systems, well, this I have said, for instance, here is determined by a ballistic growth, while here is determined by a diffusive growth for the small fluctuations. But this behavior is also shown and was discovered a few years ago in the type of models that I want to talk about today, which are these polygonal channels, and in which, depending on the geometry and the parameters of the channel, the threshold value of the moment order for these two different behaviors, something which in this case is super diffusive and then ballistic, depends on the moment threshold, depends on the geometry itself as well. Okay, I don't have time to talk to you about this. I just mentioned we recently shown that these billiards, these polygonal billiards, among many other different dynamics, even stochastic and deterministic, belongs to a certain class of universality for transport, which is the transport that is asymptotically dominated by these very rare but very long trajectories, like in the case of billiards with infinite horizon. And to describe such a class of universality, we introduce a very simple model, the most simple model that we can think of, which is fly and die, and for which not just the moments of the displacement can be computed trivially and exactly, but also the correlation functions, the time autocorrelation functions can also be computed. And we have shown here that for very many different dynamics, in particular those of the polygonal billiard, are described and are part of this class of universality. So if you are interested, take a look on this paper. But here I will show you a more defined geometry and of the polygonal channels, and tell you why these polygonal channels are so transport. As you will see, it's very counterintuitive. Polygonal channels are a type of what we call pseudo-chaotic dynamics, because the dynamics in these billiards is not well defined in the corners. If a trajectory arrives right in the corner, the dynamics is ill-defined, okay? So that corners actually in the phase space are give rise to singularities, because dynamics again is not well defined there, which are so-called conical singular points. And from a mathematical point of view, it has been shown that these conical points have very strong consequences on everything, particularly on transport. So our polygonal channels is this type of pseudo-chaotic dynamics. And you see that the corners acts as effectively as slicers of initial conditions. So if we consider an initial interval of initial conditions, like in the movie here, we see that this interval, every time that passes through a corner, is sliced into two pieces. One piece that move in one direction, and another piece that bounce back. So this is the way that trajectories disperse in this channel, And as you can see, it's essentially determined by these conical points, the corners of the billiard. So the question is how can we describe all these transport properties in terms of the geometry of the billiard itself. No? And I will show you two things that we have done. First, I will show you what we have found in terms of the statistics of the particle displacement in the case of infinite channels. And at the second part, I will show you how the properties of the statistics of the first passage time are determined with geometry. Both things have been done only numerically. This is the only thing that we have access to in such dynamics. Even though they look trivial, they are analytically not trivial at all. So we have considered simpler geometry of polygons, which are polygons that are made of upper and lower boundary, in which the slope of these boundaries is the same. So they have parallel walls, cavities. And then the billiard is, the infinite billiard is done as a repetition of these identical cells, right? So this is an opening. So in this geometry, the only important parameters is alpha, the angle that you have here that goes from 0 to pi, and the opening. So this opening will determine whether the horizon is finite or infinite. So if you take the ratio of this opening d divided by delta y, then when r is larger than 1, it means that the horizon is infinite. If it's less than 1, it means that the horizon is finite. Okay, so this is the geometry that we consider, and first we consider the statistics of the displacement. So if you compute the density of the particle displacement, you see that it depends, its details depends on whether the angle is rational or irrational, but also on whether the horizon is finite or infinite. So we have considered numerically these 4 cases, for rational or irrational angles, or for infinite and finite horizon. Now, this is the case for rational angle pi half and some counterpart of irrational counterpart of this angle, and these 2 different openings in which r is equal to or 1/2. So for the rational polygon, well, in all cases, first you see that there is a certain scale invariance. So here I'm doing this scale invariance in which I take P of delta xt as P of delta x divided by t to the gamma, to some exponent gamma. Now we see that in all 4 cases, the distribution satisfies this scale invariance, but the scale invariance is satisfied with a different exponent on whether the angle is rational or irrational. Then we see that this scale invariance fails in details. As you see, for instance, in this case, you have these peaks that as time evolves, they move away of the center of the distribution. And these are essentially ballistic fronts, right? So we have certain dynamics determined by the short fluctuations of the displacement are determined by dynamics, and then we have this ballistic front moving away of the tail. The way to see that whether these are ballistic fronts is precisely by doing a ballistic scaling. If we take delta x as delta x divided by t, then we see that all these peaks here, they do collapse at the same position, where the position is nothing but the velocity. Right? So, and then you see that while this scaling exponent for the distribution is different for the rational than for the irrational case, but it's essentially the same irrespective of whether the horizon is finite or infinite, in the case of the speed of these ballistic fronts, they seem to be determined not by whether the angle is rational or irrational, but by the horizon. You see that for the infinite horizon, we obtain here a speed of around 0.7, while for a finite horizon, we get a speed of 1/2. So this is sort of interesting. It gives us information about what properties of the geometry determine what properties of the transport, And just to see how this velocity, this speed of the ballistic fronts depend on the horizon, we have computed for many different widths of channels, the same angle, either pi half or its irrational counterpart. And we see that irrespective of whether the angle is rational or irrational, they follow a quite simple rule for the velocity of the fastest ballistic front. And it changes drastically. If the horizon is finite, you see that the speed of the ballistic fronts becomes 1/2 and doesn't change anymore. While for infinite horizon, here as you move to the right, the width of the channel becomes larger and larger. You see that you approach a case that will be ballistic when this parameter is infinite. So there is a good dependence and smooth, simple dependence of the velocity of these ballistic fronts as the width of the channel increases, while the scaling variance of the shock fluctuations is determined by the angle. Okay, we can see also how the mean square displacement behaves. In this case, the solid symbols represent the mean square displacement, or here in this case, the power scaling of the mean square displacement. And we see that, for instance, for pi half, we have that the mean square displacement goes like t to the close to 5/6. And then it grows smoothly for rational angles up to the value 2, which is the limiting value for alpha equal pi. While for the irrational case, which is these open squares, we see that they concentrate on a certain given value, more or less, and then they follow the same as rational angles after a certain big angle. Okay? So this is the phenomenology of this problem. And let me just show you what happens for higher moments, not just in mean square displacement. And you see that for higher moments, you again see for parallel walls that the anomalous diffusion is strong, in this sense that the way the different moments of the displacement scale with time is nonlinear, right? In this case, it's piecewise linear. So for short fluctuations, it behaves super diffusively with some given exponent, and then they behave all ballistic after a certain given threshold value for the order. Here are for the cases that we have studied, different values, but well, there's a good classification of it. So transport in polygonal channels is strongly anomalous. This is how some trajectories look like. This is always very interesting, for instance, because you see that the dynamics is very simple. Well, it's very simple depending on the time scales that you are looking at. No? So you see that this is position and this is time. So the particle starts moving along the channel. It starts at the origin and then it moves, bounces back, moves forward, backwards, forward, backwards, and then you see that after a while, after a certain point, which is large, after the 2-3 millions of collisions, there is some sort of structure that is repeated. Then you think that this will end up there. So if you go to higher times for the same trajectory, you see that then at some point, this behavior changes into something completely different. So you have the same structure, but then it bounces back in a different oscillation, much wilder oscillation. Then again, you think that now everything is more or less regular, and you go to 10 times longer times, and you see that what you see here is here, and then all of a sudden you have a very long flight. This is for the finite horizon. So these are not infinite trajectories, these are trajectories that are bouncing in the billiard, but then they do something else, and then they repeat again. But if you go to larger scales, then you see that these repetitions again are different. So this is a very weird behavior of these polygonal billiards, because the scale seems to depend on the time at which you observe, which is a property of aging. So I find this very interesting. Now, the other thing, and I will finish very soon, the other thing that I want to show you is the statistics of the first passage time. So imagine, I will go through quickly. Imagine we consider now a finite channel. And we ask for, we start all trajectories in the initial central cell. And I ask myself for the time at which a given trajectory leaves the channel. It reaches its boundaries. No? A channel of length L, so I ask, what about this time? What this time is? I repeat this for many trajectories. I do a histogram, and this histogram is what is called the first passage time distribution for the escape of the trajectories from the channel. And this first passage time, as you know, is a very important observable. In particular, the mean first passage time is very important in many different problems of random walks, but also to many people uses pretty much to study the cell kinetics for macromolecules moving in the cytoplasm of the cell, and so on. So we asked about this question. And the surprising thing, I will just go through the, well, you see that these distributions for the four cases that we consider fit the tail. We don't not expect to fit this part, but the tail is fitted by the first passage time distribution corresponding to a Brownian motion in a semi-infinite line. And that is interesting because then we can think of certain parameters. For instance, the mu appearing here is called the persistent exponent. Tau is simply a time scale, but mu is an important exponent in physics and in the community of random walks. So we see that this mu have different values depending whether the angle is rational or irrational, no? And in particular, and this is very surprising, for rational angles, in this case for pi half, the persistent exponent is less than 1, while for irrational it's larger than 1. And that has strong consequences on the statistics of the first passage time, because this means that for rational cases, the mean first passage time diverges. It doesn't exist. Okay, so that's really very surprising. So surprising that we look also at the different angles numerically, and you see that the persistent exponent is persistently below 1, smaller than 1 for certain simple rational numbers, while for the rest of rational angles, but for the rest of the angles is quite above 1. Right? So this is very surprising. This means that for all these rational values, the mean first passage time do not exist. And for these other cases, since it is smaller than 2, it means that the mean first passage time exists, but the variance it doesn't exist. So we expect very wide fluctuations over there. And we're trying to understand why. This is an interesting question. This value here is singular. There is no smooth transition between rational and irrational. If you compute more values in a finer scale here, then the only angle that becomes like this is rational. Obviously, not all rationals have this property, but just the simple ones. And we would like to understand why. I think this would be, in terms of periodic orbits, the structure of the periodic orbit should give us an idea. And this is about the final results, precisely that we want to study well, there are some information that we already know about the polygonal channels. There is a huge mathematical literature, the Russian school particularly, about whether the periodic orbits for rational angles are dense. This has been proved also that they are typically ergodic, but for irrational angles, it's not well known. So there is an obvious connection between the structure, at least I expect, of the periodic orbits and the complexity of the transport that we observe. There are some open questions that I am very interested to investigate in such problems. One is a general open billiards as model of scattering systems, some stochastic extension of billiards to study thermal equilibrium inside the billiards themselves, or billiards with interacting particles, or some generalizations of certain mathematical schemes in which one can study this analytically. I'm very interested in all these things, and With this, I thank you very much. I mentioned the people that has involved in different questions around this problem, and also the Spanish and European funding for this research. So thank you very much.
Thank you very much, Carlos. Questions?
Can I ask one?
Please.
Yes, absolutely.
Carlos, thank you for interesting presentation. I just wanted to ask you maybe a sort of a follow-up question. So, as I correctly understand, you discussed the particle movement when you have the fixed number of particles. So you start with one particle and you end up with one particle. I don't know about physics, what are the processes in physics, but with money, you have credit money when one unit of currency, like €1, multiplies to many. So I don't know, is there a sort of research on the dynamics when the number of particles multiplies on the way of the movement, you see?
So in this, okay, let me try to understand and to reply to your question. In billiards in general, you consider that particles do not interact. And therefore, this is essentially a single particle problem. You study one particle and only one particle. You can study at very long times and then do the statistic in times, or an ensemble of trajectories and do statistics of the ensemble of trajectories. The particles, they do not multiply. Maybe what you mean is, how do I go back? Yes, like this. Maybe you mean this movie that I showed you to, no? This essentially here, this is a set of initial conditions that are along this line.
Yes, but they like the entire line is still preserved. But I mean, if like the line would become longer, or so the multiplication, I mean, not the decomposition, but multiplication, I mean, in length or like.
Yes, it sounds interesting, and interesting that it could have some, some connection with other problems like in finance or economics.
It's a separate discussion, but just wanted to know because it can actually add a lot.
Yes, yes. Thank you for the question. Maybe if we discuss through email, it would be interesting to me as well. Yes.
Thank you.
Carlos, let me ask 2 questions. The first one, in your last figure with magic rational numbers, do you see some regularities with these numbers?
Well, the regularities that they indeed corresponds to simple rationals. You see, this is pi 6, pi 5, pi 4, pi 3rds, no? And from some of these ones. I think my idea is that there must be some regularity in terms of the genus of the phase space corresponding to the polygon. Because this angle precisely for a closed polygon, that angle will determine the genus of the phase space, and that it's different for simple rationals than for non-simple rationals, right? So this is something I am investigating to first to try to understand why rational angles are so different than the others, and why only few rational angles, the simple rational angles, appear here. Because here there is an infinite number of rational angles, obviously, but just the simple ones have this property. So yeah, I think something in terms of the units. From a physical point of view, it has to do with the correlations. But then the question remains, why correlations are so different for these angles and others?
You shown a figure where this specific horizon appears. First, you shown this figure in normal, let me say normal scale, and then in another scale. I found this picture. Yeah, here's this picture. I found it in your paper and looked at it, enlarged it as much as I could. And it seems that at the right, you have prior to this point marked by dashed line, that you have other attempts, to make a peak. Your graph pretends to show a peak a bit earlier than 1/2, and the first break in tendency is even somewhere in 0.25. So I mean, that does it indeed indicate some additional scale, or it's nothing? Some kind of artifact.
Yes, you mean these artifacts around 0.25?
Yeah, and it seems that, if you just put a piece of paper to the left part.
Yes, indeed, they do also align. Indeed, this is the case. I think, in my opinion, what we have here is that the large fluctuations, those that determine the tail of distribution, are ballistic fronts, but not just one ballistic front, several ballistic fronts that move at different speed. So for instance, this, as you very carefully observe, this is the speed of these ballistic fronts, where you see that all of them align, it's 0.7, but here you have another structure which moves ballistically, because on the ballistic scale, they do align as well. And here you have another, and here, this deep, you also have another, no? So indeed, this is why I talk in the next figure about the fastest ballistic front, because in principle, you have many. And I think indeed that for all of them, the scaling invariance will be like this, of ballistic fashion. But there will be a certain prefactor here that depends on the velocity of the fronts. So for me to try to understand the behavior of this tail, which I didn't say, but it looks quite exponential, like in this case. But the good news is that somehow I have the hope that by doing some sort of summation of periodic orbits, I would be able to say, okay, these periodic orbits determine these trajectories with this speed. These other periodic orbits determine these ballistic trajectories with this other speed, and so on and so on. It's a difficult problem, because for chaotic dynamics, these are more easier. The phase space is more regular, but for integrable dynamics, it's very difficult. But indeed, I think there are an infinite, in principle, if not many, many ballistic fronts. And obviously, the fastest one is the most important for the large fluctuations, but it would be really great to understand all of them. Yes.
Well, thank you so much that you found time traveling.
Yes.
Have just a couple of days in Paris and have a nice flight back to Madrid.
Thank you very much. Thank you very much. I'll stay here for a little bit more, but then at some point I will need to leave to head to the airport. So I'm very sorry if I'm not able to listen to talks.
Yeah.
Thank you very much.
Who will be in touch, and we continue, because we gather based on more on people than on stories. And today, Igor, please teach us about economical problems. Some example of mathematical economics. Floor is yours, and it would be nice if you can cope it with back in 25 minutes, but take your time.
My voice is okay?
Yes, it's
great.
Okay. Thank you. My presentation is about some unified approach to the two concepts of modeling in monopolistic competition. One concept is market equilibrium, and another concept is social optimality. So market equilibrium means that the producer maximize the profit and social optimality means that we try to clarify the role of the government, so maximize so-called the total utility under labor balance. And these concepts seem completely different, but we find some link between these two concepts. Last year in this conference, I presented the case of two countries, and now I start from this case and then to tell something about the generalization in the case of several countries. Several years ago, Sergei Kokovin from High School of Economics, excuse me, there was some idea that these two concepts leads to the same optimization problem, but if we consider not revenue but utility, then so in equilibrium we must consider the revenue, and in the optimality, social optimality, we must consider the utility, and we will lead to the same structure of the problem. And we studied this hypothesis and generalized this to the international trade for any kind of production costs. So in monopolistic competition, there are two concepts of market equilibrium and social optimality, and we find the unified approach. So market equilibrium is very, very popular. This is the information about today. Some number of citations of these very famous articles. And the monopolistic competition trade model means in our framework something like this. The consumers are identical, and every consumer has only one unit of labor, and everything can be calculated in labor, everything, consumption, output, prices, and so on. Firms are identical but produce almost the same goods. The demand function is additive separable. Number of firms is big enough, and we will consider the concept of mass of firms, and the concept of free entry, labor demand, and so on. And let us consider firstly the case of two countries, big and small. The notation is that this is the number of consumers in H and F, big and small country, the mass of firms, and the X chi L is the amount of the variety produced in country K by the firm I and consumed by a consumer in country L. So it is individual consumption. PKL is the corresponding prices. In first country, in big country, the wage rate is W, and in small country, it is equal to 1, normalized to 1. And the subutility function is, as usual, 0 in 0, strictly increasing and strictly concave. So the problem of the representative consumer in this country, in each country, is maximize the total utility under a budget constraint. By first order condition of these countries, we find the prices, but more not prices, but inverse demand function, where lambda is corresponding Lagrange multiplier. As to producer, then we consider the case, the case when we have trade cost of iceberg type. So the size of firm in each country is something like to produce to the home consumers and to the foreign producers. And tau is this trade cost of iceberg type. The profits are, as usual, the total revenue minus total costs. And here we substitute the inverse demand functions, and this is so-called revenue per consumer. This is revenue per consumer depends from the Lagrange multiplier. And another labor balance. The total labor in economy is equal to the total costs in economy. Some interpretations, what means so-called not number of firms, but mass of firms. Suppose that we have gas stations in very long road. We are not interested to the number of these stations, but we are interested to the length of the road. So, and another, what about the costs, transport costs or trade costs of iceberg type? To sell one unit, it is necessary to produce tau multiplied this one unit. It means that during transportation, production melts like an iceberg. So let us consider, of course, as usual, the symmetric case. It means that we will not have this I, and this is completely the same, but without I, without index I. Trade balance is something like this. Social welfare, total utility, when we substitute labor balance, we have these formulas. And now let us consider the concepts of equilibrium. So what means equilibrium? First order condition for producer, second order condition for producer, free entry, which means zero profit. So the definition of symmetric market equilibrium is a bundle, the individual consumption, the corresponding prices, the Lagrange multiplier, the mass of firms, and the wage in the big country, such that we have rational consumption conditions, rational production conditions, zero profit, labor balance, and trade balance. As to symmetric optimality, then we maximize the social welfare under called labor balance. So the symmetric social optimality is the bundle of individual consumptions and the mass of firms, such that rational welfare conditions, which means first order condition and second order condition, and labor balance. So you see that this problem seems, these two concepts seems rather different. But let us introduce, as usual, the concept of elasticities of function. Then let us consider the total domestic consumption and the firm sizes. And let us introduce this function, and let us consider these two functions in different points. Suppose that this is equilibrium. You see this is equilibrium, and consider these two functions in these points, and this function in another points. And now we try to find some equations that seems the same, but we calculate this function in different points. And the first proposition is that in equilibrium, so it is not first proposition, it is first part of first proposition. In equilibrium, the elasticity of revenue and the elasticity of total costs has this equations, and where these coefficients are completely this that I wrote before. So this is the result for equilibrium, and the result for optimality is completely the same by the form. If we write here instead of equilibrium optimality and instead of revenue subutility. So this is the second. Now you will see the second part of this proposition about optimality. So this is first part about equilibrium. This is second part about optimality. It seems completely the same structure. They have the same structure. So this was the result 1 year ago, and the corollary of this proposition is something like the corollary is, these corollaries are the generalization of well-known concept that in equilibrium, elasticity of revenue equals the elasticity of total costs. So now we see that convex combination of elasticities of revenue in different points is equal to elasticity of total cost in each country. And in corollary, in some sense, the same structure, the convex combination of elasticity of elasticities of subutility in 2 points is equal to the elasticity of total costs. Of course, is rather strange to interpret these coefficients. But another proposition give us the possibility to have generalization of this concept, the inequilibrium elasticity of revenue equals the elasticity of total cost, without using this inconvenient coefficients. So if we consider not elasticity, but inverse elasticity, not 1 over elasticity. So this is the result that this convex combination in terms of firm size and this the items in this firm size. So this convex combination of inverse elasticities of revenue is equal to inverse elasticity of total cost in each country. And this was the results of 1 year ago, and now we will try to generalize. Let us consider the case of several countries. The case of several countries, K countries. K is fixed, and now this is not mass of firms, and the mass of firms, you remember, it is endogenous. We will find endogenous. So L is the number of consumers in each country. This is the individual consumption. This is individual, the corresponding prices, the total output in firms for each country, and so on. And this is the wage in every country. Then the problem of representative consumer in each country is the maximize the total utility under budget constraint. As usual, first order condition give us the inverse demand function by this equation. So this is inverse demand function. And now let us consider, as usual, the symmetric case. So everything is before without the index I. So this is the total output of the firm K. This is inverse demand. This is the profit. When we substitute in this profit, of course, inverse demand function. And as usual, we have labor balance, trade balance, which means export equals import. And the definition of symmetric market equilibrium is that it is these bundles satisfy to these usual conditions: rational in consumption, first order condition and second order condition for producers, free entry, labor balance, and trade balances. Trade balances in each country. Trade balances in each country. And social welfare can be considered as total welfare in the economy. Substituting the labor balances, we have this formula. And as to symmetric optimality, then the symmetric optimality is this. The social optimality is this bundle satisfied to welfare condition, of course, second order condition, of course, yes, and labor balance condition. And what about the unified approach to this? And we find this rather simple function. It is only number of consumers multiplied to some function in individual consumption. And when we will choose the special function, then we will receive our results. Let us denote usual production and the firm size in equilibrium, this, and firm size in optimality, this. Let us denote these coefficients, these two coefficients, where this kind of coefficients are the value of this universal function calculated in different points. So here we have the revenue per consumer, and here we have the utility. So, and as usual, you remember what means the elasticity, and let us assume that the market equilibrium and social optimality exist, and moreover are unique. So we will not consider the question about existence and uniqueness. So our first proposition is that in symmetric market equilibrium, we have this formula. So the elasticity of revenue is equal to the elasticity of total costs with these coefficients. And in symmetric optimality, we have the same kind of formulas, but using the same kind of coefficients, but calculated in another points. So this is the main proposition, the main result of this presentation, and corollary is the two parts of the corollary, which are the generalization of well-known facts about this, that equilibrium elasticity of revenue equals elasticity of total costs, while in social optimalities, the elasticity of sub-utilities equals the elasticity of total costs. So this is the corollary, that the elasticity of total costs is the convex combination, and this is coefficients of this combination, the convex combination of the elasticities of revenue in each country, and in social. This is, of course, not only market equilibrium, but the symmetric market equilibrium. And here in symmetric social optimalities, the elasticity of production costs is the convex combination of the elasticities of sub-utilities of individual consumptions. So what we find? That the structure is the same, and we find this universal function, the universal function. And another about discussion that we try to generalize our result about for two countries in equilibrium, for several countries without using the this universal the values of universal function in different points. And it is possible, so this is the result without a universal function, very, very clear to understand what it means. And of course, if we divide everything in this denominator, we have that 1 over elasticity of total cost is the convex combination of the 1 over elasticity of revenue. And of course, the last proposition must be the second part of this proposition about social optimality. Unfortunately, it is not possible to write this only to change EQ na opt, so not equation but optimality. It is not possible, but some result we can write, and this is the next slide. So this is not here is a rather elegant formulas in terms of elasticity, and here of course not elegant, so this is not good, of course, but we use here even the number of countries. So this is the last formulas now, and the last proposition. And the conclusion is only about what we do, what we did, and what we plan to do. So, thank you. Thank you very much.
Thank you very much. Questions? Good time for questions.
Just a small question. Maybe it's more technical. Igor, can I ask you?
Mm-hmm.
And did you derive formulas manually, or did you use some software with symbolic equation solving? Should I ask in Russian? Or?
No symbolic, no, manually, because symbolic, something like the programs reduce cannot help, but not a lot, because it is the problem in monopolistic competition, yes, that the reduction of the formulas, so it must be some artificial intelligence, and maybe after several years it is possible to calculate this without any person. But,
thank you.
But not now. Excuse me.
Unfortunately, colleagues, we do not have time for further questions. So thank you, Igor, again for a nice presentation. And let's go to the next talk.
So stop the presentation, yes?
Genrich, now everything is yours. What I can give you, and starting from this nice picture, please continue.
Sasha, thank you very much. Thank you for inviting to present at the session. Representing Bank of Russia, all I will be talking here about is only my personal opinion and not a reflection of any position, official position of the Bank of Russia. So in considering this disclaimer, let's proceed with the topic. It won't be as complicated and multivariate like what Carlos said, and it won't, though it's somewhat similar to Igor, like it will consider several countries, but it will be hope it will give you some ideas, maybe in your research, maybe. So, and the idea should come from this so-called Benford distribution. I will briefly remind what is this, and let me proceed in the fashion so that you can grasp the idea and understand what's the implication. So, starting from the findings, I would like to highlight that so-called the compliance to Benford law might be a sort of default rate or probability of default determinant. And though before it was just the indication of fraud, not the indication of credit risk, but fraud, so-called operational risk. So if we dig deeper in terms of technique or metrics, it turns out that mean absolute error is more informative than root mean squared error. And what's more interesting is that there is a sort of U-shaped dependence. I would gladly accept all the criticism on behalf of econometrics that is used, because we have nothing better, no experiment in economics, but the best what we have, and also it's not agent-based model. So that's considering these limitations, I would like to proceed. So if you would blame me on this, I would fully accept this. So let me briefly introduce you, let's say, to the highlights. The Benford law, coming to the Newcomb Benford, I'll explain it a little bit later. It actually is applied to very many domains, to verifying elections, in the data on viruses, infections, to fraud in finance. But same time, there is so-called P2P, peer-to-peer lending, peer-to-peer, the popular online platforms where you can act as a sort of a lender, borrower, and earn some money, a sort of a novel fintech innovation. And there is a person, Asror Nigmonov, who already investigated the data of the European peer-to-peer lender Mintos and the US lender, the Lending Club. But he did not look at the Benford law compliance, and I would like to close this gap because I think it's at least interesting and maybe it will be useful. So I'm not going to talk about the PD, probability of default model determinants. There is a large set of such papers, but none of them include the compliance to Benford law. So what is Benford law? Let me just briefly explain. It dates back to 150 years ago. We need to look at the first digits of the number. So actually we have only in classical arithmetics with the base 10, we have 9 first digits, and the Benford law, the PDF, the probability density function that's illustrated in red here, it is the frequency, the logarithm of 1 plus inverse to the value to the first digit. So that's it's a subtype of the exponential distribution, the randomly declining probability. And if we have some data like the black one that corresponds to the data that we'll be talking about, we can use either mean absolute error or the root mean squared error between the values of the frequency. Of course, there is a large set of discussions and there is large literature on whether these metrics are really informative, because we have not a sort of we might have a great underlying data, but actually the whole distribution is fit to only 9 points, to 9 probability concentrations. So that's where H is the actual histogram or actual frequency, and F is this theoretical frequency. So I'm not going to discuss the limitations of these metrics, but they are the most conventional and the most popular when talking about the compliance to Benford law. So what is a sort of research idea? Research idea is to look at this Mintos data, and actually I'm presenting here the URL. For those of you interested, you can actually click on it. You can, it requires some simple registration. It doesn't require money if you are not going to be an investor, and you can download the entire loan book. For those of you who've dealt with the data processing yourself manually, like Igor did, so it is mostly 3 gigabytes of data. The archive at the moment of download, it was mid 2021, comprised of 71 files. Each file comprised of 500,000 entries, 500,000 records loans. So in total, we have around 3 to 4 million loans. And the data is quite peculiar. All loans said to be offered in Russia have 0 default probability, like super reliable, super creditworthy. Loans offered in Zambia, each is not paid back. The default rate is 100%. There is, of course, as you might challenge, why should you then give any loan to a person in Zambia if you know that by a priori probability it's 100% default? This question is left for our thought, and that's just a visual demonstration of the data for you to feel it. So the black line is the volume, so it reaches at maximum 4 to 6 million euros. For us personally, it is a large amount. For the financial institutions, it's a tiny amount, while each particular loan is roughly 100 euros, 20 euros, but there are some mortgage loans for thousands of euros, for dozens of thousands. So, and the dashed red line, it is peculiar default rate. It is not the default rate at this date. This is the origination or issue date. So it means loans offered mostly in 2019, they demonstrate the default rate close to 100. Those offered on the eve of 2018, they had the default rate like 20%. But we do not know in which year it happened. So the data comes, the maturity dates go to 2027. So probably these defaults might have occurred in 2020 or somewhere, but the data does not report this default date. So there is some limitations to this data, but it's nice that it is publicly available and we can exercise ourselves with it. So what we know, there is a set of indicators that we can have, and mostly interesting for us is that there is the initial loan amount. So the mean amount is about actually 4,000 euros. It's one taken overall with mortgages, etc. There is the loan maturity. So if we calculate it formally between the reported close and issue date, it's around 2.5 years. And the loan to value proportion, it's a sort of indication of how reliable, how risky is the loan. So loan is the amount that we offered, and value is the value of collateral. And there is a flag. It seems to be the flag of the collateral presence, and like 43% of the loans, they have some collateral that is only 30%, produces 30% of the, so actually the discount, the haircut to the collateral is 70%. So loan to the collateral value is 30%. So it seems that the loans are quite collateralized, so they are non-risky. The mean absolute error and root mean squared errors for Benford law is like 11 and 20%, but these numbers, they do not tell you much because you should see the dynamics or data dispersion, data variation, and overall we have 1,200 observations. These are aggregate observations by country and by the lender, because this peer-to-peer lender, it somehow aggregates loans. So these 1,000 observations is the aggregate from 4 million loans, because we need observations that consider, that represent the compliance to Benford law. A single observation, a single loan cannot tell us anything about the means, about compliance to Benford. We need a series. So what I would like to present you. For instance, if you look at mortgages that are also available in the data, you can see that, for instance, mortgages were often offered, and these digits come from the original currency. So when I presented you the volume dynamics, it was converted by the applicable exchange rate to the local currencies, but the figures here are in local currency. So as you can see, for mortgages, compared to original Benford law, there are more mortgages offered with the number of starting from the digit 2 and a little bit less starting from digit 1. And so what we can see, this incompliance is reflected in higher dispersion and higher mean value of the mean absolute error to Benford law compliance for mortgages. As for other types of loans that are reported, like short-term personal, some pen broken, like also like peer-to-peer lending, car or auto loans and other. So actually for mortgages, the dispersion is the largest in terms of the Benford compliance. And as you can see for the entire data set, what we see that the incompliance in terms of mean error, the mean absolute error, that is black line, it radically dropped in like 2012, but actually it dropped as for the data offered after the date, and actually we don't know when it was, let's say, aggregated, securitized by this peer-to-peer lender. As for the root mean squared error, the decline is more moderate. Maybe that's one source that drives greater dependence of mean absolute error and the default probability. But what I would like to show you, the codependence of principal indicators. So we are not, unfortunately, we can't see a nice trajectory with the quite vividly, with a quite dependence in between our conventional probability of default indicators like the loan size. We would think that actually the larger the loan, the less it's prone to default. The longer the loan is, generally, it's different regulators say it should be larger. The default rate for the more longer contracted loans, but Merton told that it should be negative. So initial loan to value, it seems that the larger the initial loan to value is, the loan is riskier, but the linear trend is declining. So that's why we sometimes try to fit the quadratic term, but actually this fit is quite unreliable. So it's driven by some outliers on the tails. So when cutting them off, it we lose most of the significance for these variables. And generally, the presence of collateral on average is mostly the expected one, the negative. The more collateral we have, the less the default probability is. And what's strange is about the codependence of collateral and the initial loan to value, that actually in case when we have, and that's the mean collateral because we aggregated the data, as you remember, by countries and by the lenders. So it means that's why we get the proportions, not only 0 and 1. So what we see that actually those that have the higher collateral, it has also the larger loan to value. It means the collateral is there, but it's actually mostly the riskier loans that have the collateral. Maybe that's the so-called typical indigeneity, that the collateral is asked because the loans are risky. So, but let's look at most interesting facts. We map errors, the compliance to Benford law, the mean absolute error, the root mean squared error for the entire set of loans and only for the category of other loans. In these graphs, of course, the black line and the red line, they are not quite visible, though for other loans, the dependence is more pronounced. That's why we look separately at the trends. At the trends, let's say we zoom in this part and we see that actually for the mean absolute error, we have this nice inverse U-shaped curve. It's also present for the root mean squared error, but it's symmetric for the pooled loan and asymmetric, I mean, for other loans. That's the default rate distribution for you to see that it is bimodal. It's not like the one that Carlos presented, that like assumption of normality. So it's not normal, it's bimodal. And formally, when we look at the regressions, we see that in some cases, only for the pooled loans and for other loans, we have the significant levels and squared levels of our variables that yield us with this inverse U-shaped. So that's the variables that we mapped in our econometric equation. And that's where we derive that the optimal, quasi-optimal, I mean, when you look at mean in this red line, the mean value that produces the extreme value of this inverse parable, we have in around 50. So actually, what are the findings that maybe you might find interesting and that you might look at? So that this mean absolute error tends to be more significant factor than the root mean squared error. And what we find is that there is actually this so-called inverted U-shaped codependence of the error, and the default rate for this particular Mintas data, though it has some limitations, the data may be not too trustworthy, and like the list of loans with Zambia and Russia, but as we do not have the default rate date, we cannot link it to macro environment. So, but actually what I wanted you to know is that or remind you about the Benford law, maybe in case when you deal with some particular data and some particular human generated data, you might find it interesting to map it to Benford law, and maybe it would be a significant driver for the indicator of your interest. So I would like to thank you for attention, and if you have any questions, you can answer.
Thank you very much, Genrich. Questions, colleagues, nice time for questions. We are in a virtual world, and if we lose a Genrich right now, so how can we ask questions?
At least via Sasha. Sasha is the great coordinator, so via you we can always stay in touch.
Yeah, it would be nice to stay in touch, independent of the presentations. But I have a question regarding what you said. As far as I understand, but I'm sorry if I'm wrong, that the success is that this measure related to Benford law correlated with a standard probability of default. And as I can derive from these black and red curves. I don't understand. Do you have information in the data set? It seems that you have information in the data set regarding the default of each particular loan.
Correct.
So can you test the hypothesis that deviation from the Benford law is correlated with factual defaults?
And that's exactly what is done here, because that's the default rate, the proportion of actual defaults. Why it's proportion? Because the aggregate per country and per lender. So that's the proportion. So each dot, each round here, its circle, stands for some particular date, for some particular country, that there was some measure of incompliance for loans given at that date, and for some default, actual default rate of that particular set of loans. So it's exactly how I acknowledge all the tricks with econometrics, like there might be indigeneity, there might be, we cannot have real experiment, but that's exactly about this correlation, co-movement into factors that are by definition should not be anyhow, let's say, correlated with the errors, like for the indigeneity. So that's actual default rate.
Sorry.
please. Sasha, I don't hear you. Is it me who doesn't hear, or Igor, do you hear me?
Yes, I hear.
But I don't hear Sasha. I see.
I'm sorry.
Now I hear you.
Was lost.
Yes.
Because of the batteries in my earphone. Now everything works. Could you please specify once again the numerator and the denominator? So what you divide?
So let's say the equation. Yes, on the left side there is the actual default rate, and on the right side there is the distance measure and its squared value, and this distance can be mean or root mean squared error. So, and this distance is exactly about the compliance to Benford. So that's how we compute the, so here it's just the bivariate scatter plot, two-dimensional scatter plot. And here we control for some other factors to net the impact of this compliance. That's just like here is a single variate regression. That's a multivariate analysis. Just that sort of way, you see.
Yep, it's really very interesting and exciting and unexpected. Let me say, to some extent, unexpected. What I would say economists do not like, but probably it's reasonable to split the whole database into parts because the database is huge, the number of digits is small. And if you, well, you can do it either randomly or it's contrary, trying to eliminate some outliers. But if you split it randomly, you would expect to see to some extent the same results, probably not so stable because you split it, so the number of observations is less. Just to see that it is empirically nice. Still, it is absolutely impossible, absolutely unknown what the mechanism stays behind. It's always a question regarding the slope, because so what is the explanation that? Just conclusions that say it's not about what you said, that loans of such type.
So, Sasha, thank you. If I correctly understand you on this fundamental question, that generally, of course, my interpretation is just another hypothesis to set because this data has no opportunity to verify whether I'm right or wrong. But the initial hypothesis was that the more the data is in compliance, the higher the default rate is. So we expected the single, not U-shaped, but linear upward sloping dependence, because conventionally, the more incompliant the data is, the more fraudulent it is. That's the finding of the auditors. So I thought that maybe with the credit risk, we have the same upward sloping linear trend, but at least for this data, maybe it's the case for other data. It is not that linear. It has inverse U-shaped curve. So maybe the quite strange and very compliant data is actually quite trustworthy, but something in the middle actually deserves more attention.
Well, thank you very much. Other questions?
Thank you.
Well, now the last but not the least, and let me say that Anna Muratova, who is going to present, it was very difficult for her, so first time for her was extremely convenient, and it was announced just prior to the conference, but she I don't know, went through all problems, I don't know, through rain, snow, and now she's with us. So Anna, please, you are the boss now.
Hi. My name is Anna Muratova, and I will talk about our work with Dmitry Ignatov, evaluation of the influence of movie title texts and features on the movie rating prediction. In our previous papers, we have applied various machine learning methods for demographic problems, and good results were obtained on a neural network model that processed both features and sequences. And it was interesting to apply a similar architecture to the task of predicting ratings on a movie lens dataset. There are several movie lens datasets of different sizes, and also they are slightly different in their content. And we have chosen the movie lens 1M dataset, which contains about 1 million movie ratings. The aim of this work was to evaluate importance of semantic information of titles text for the neural network model for predicting movie ratings. A multi-channel neural network model was developed with several separate channels for various features. And in addition, to improve the predictions, a channel for extracting semantics from titles text was used. Additional features were also created by words of movie titles. The influence of additional semantic information on the predictions has been also investigated. So first, I will talk about the data set, then about the structure of the neural network, and after that, the results of rating predictions will be given depending on the used set of features and title. The advantage of the movie lens dataset is its typicality, common characteristics with datasets found in other tasks. So a model that works effectively on the movie lens dataset can be applied to other datasets with appropriate adaptation. This movie lens 1M dataset consists of 3 files: users, movies, and ratings. Here we can see the structure of the files. Users file contains features such as user ID, gender, age in one of 7 ranges, profession, occupation, and postal code. Movies file contain features movie ID, title of the movie, year of release, and genre, such as drama, comedy, children, and so on. And several genres can be specified at the same time. Ratings file contain about 1 million movie ratings assigned by different users. This file has features such as user ID, movie ID, rating from 1 to 5, and a timestamp. Movie titles were typically preprocessed to lowercase, and words such as n, the, and so on were removed. Then after that, integer words encoding was applied by a dictionary of all unique words in all the titles. The maximum title length was limited to 12 words. Shorter encoded titles were padded by zeros. Also, additional feature decade was created from the year of the movie. It is a third digit of the year of the movie. We suppose that user preference may depend on the decade of the movie. So the year number is too detailed for that purpose. For certain features, we used the following encoding. Gender, for example, was encoded to 0 or 1. Zip code was cut to 5 digits and encoded to integer values beginning from 1. Every genre was encoded to 1 if movie belongs to this genre and to 0 if not. And also, yes, any movie may belong to several genres at the same time. Other features such as profession, age, and others were encoded as integer in the source data. The movie length dataset was split for training and test data as 90 to 10. The neural network model for rating prediction was developed. The structure of the model is presented in this figure. So for every feature, a separate embedding layer is applied. And for titles, embedding applied with input length equal to the maximum title length in words, which is equal to 12. Then embedded titles are processed by dense layer, which is fully connected layer with activation function remove. After that, embedded features and titles are concatenated to a merged layer, and then they pass through 3 dense layers with dropout and batch normalization. The last layer is dense sigmoid, which performs classification into 5 classes as predicted ratings. This model structure allows to evaluate importance of users and movies features, and also movie title for the task of movie rating prediction. The model was applied for different feature sets, and performance was evaluated with Maya and RMCA metrics. The mean absolute error is a risk metric corresponding to the expected value of the absolute error loss. So here we can see the formula for this metric. The mean square error function computes mean square error, and the root mean square error function is equal to the root of the mean square error. Here we can see the formula for this metric. The experiments for evaluation of different features influence on the movie rating predictions were made. The baseline feature set includes only user ID and movie ID, and model performance on this feature set was defined as 100%. The model performance for a different feature set with addition to the baseline feature set was considered and compared in percentage to the baseline feature set. The different features include decade, gender, age, occupation, zip, genres, and title. Table presents percentage improvement of Maya and RMCA metrics. And these values are average values of 5 runs of model training and prediction with the same parameters. Here is a diagram of influence of different features together with user ID and movie ID. We can see that the feature genres has the highest influence on rating prediction for both Maya and RMCA metrics. The next 2 features are decade and title. Percentage improvement of Maya and RMCA metrics was also computed for a feature set by by sequentially adding the most important features to the baseline feature set, which contains only user ID and movie ID. The results are presented in this table. It can be seen that the values of Maya and Hermessier decrease by adding another important feature. The best values of both Maya and Hermessier are obtained with all of the features together. Compared to user ID and movie ID, the percentage improvement for Maya is 3.21% and for Hermessier 2.82%. The best value for Maya is 0.61 and for Hermessier 0.92. The influence of the title on rating prediction was also considered. Since the best results for Maya and Hermessier were obtained with all of the features together, let's compare these results with all of the features without title. So here without title, here with title. We can see results in this table, and it can be seen that the title has a noticeable influence on metrics Maya and Hermessier. The percentage improvement for both metrics is about 3%, and for all of the features with title. And this is almost twice better than with all of the features without title. So in this paper, using a neural network model, the influence of features and title text on the accuracy of predicting movie ratings is shown. The task of predicting the rating of a movie for a user belongs to recommended systems tasks. And based on the rating of prediction, the user can be recommended movies that he would rate the most. The prediction takes into account the features of the movies, the features of the users, and as shown in this work, the text of the title of the movie. So that's it from me. If you have any questions, Ignato, Dmitry, and I will be happy to answer them.
Thank you so much for the talk. Our colleagues, questions?
Anna, can you show, for instance, a slide, the one before the conclusions? Yes. Could you please explain once again? Maybe I missed some part. So, as I understand, you say that figures in bold are better than figures that are not in bold. Is it correct? But you say that as the error improvement is larger for the bold values, then, like for instance, title is important. But what I can't get, could you please explain? So the particular error value, it declines, like 0.6234 versus 0.6146. So the error, so you mean the error is decreases? I see.
So the less, the better.
I see. I see. Thank you.
Anna, as far as I understand, so the semantic, the title matters. Okay, and based on this, you can predict. Can you say in words, I mean in normal words, in a language, in the way people speak, what is important, what kind, what words, I don't know, what expressions, could you somehow speak out what do matter? I mean, what affects, what indeed affects the future ranking?
As I understand the question, you mean how we can see that the title is important in our
No. What
maybe to give an example of some movie to understand what for instance, this is good, this is bad, or something like Hobbit is good and mathematics is bad. I don't know.
May I just slightly reformulate the question for Anna? It's something like in Shapley values when we analyzed ordinary features for predicting a particular objects class, which feature is the most important. And here, by those features, the colleague means separate words. For example, the movie entitled What's Eating Gilbert Grape contains several words. And what are the words which are important, maybe, or somehow implicit genres which are contained in such words. Maybe they are important somehow. Did you do this study? You can simply answer.
So, for example, user preference may depend on some typical words in the title. So we consider title as separate words, and for example, some words may be more typical for some users. So that's how the title will play its role in better prediction. I don't know if it answers the question. Maybe Dmitry Ignatov can answer this.
Yeah, it seems that we did not do that at the moment. We did not extract particular words along with their ranking. So it was rather a general influence assessment. So we added something else to user ID and movies ID, which is the baseline for collaborative filtering. So here you can see the difference for including title as a whole. However, I agree with Alexander that it might be interesting to see the distribution on words, because it might be not only the quality increase in general, but in local, it may be the quality decrease if we take into account some particular words, I believe. So it's an interesting question, and I believe it's good to answer in future.
Yeah, it's interesting.
Well, thank you very much, Anna. And well, unfortunately, I have to close this session, but I would say as characters in movie probably not probably analyzed here in this talk, that probably this session, this meeting will be a beginning of now let me say beginning of some cooperation, and so it's nice that we met, we saw one another. Now we are sure that we are alive, we work, and let's hope we'll see in the future. Thank you, Dmitry. It's nice to see people. So if everybody wants to switch on, somebody switch on camera, it's not a bad idea. Well, so if somebody wants to say something, please do. But our official part is over.
Sure. Thank you for a nice tradition. For me, it's the second conference Max Pro that I participate in, and I really enjoy it. So thank you for the initiation, and Happy New Year.
Happy New Year.
Thank you. I believe it's good work that organizers did, and I'm impressed by the number of papers in comparison to the previous years. I know it's now the growth stage of the conference, which means hard work, and we need to face new challenges, and I hope to contribute at least minorly to the process. So, and wish this success to the whole event. And I'm proud that the organizers managed to survive, to organize such an event in such pandemic conditions. Very hard time. Thank you.